Welcome to Pre-Calculus. Today we will investigate graphing rational functions with horizontal asymptotes, focusing on strategies for locating horizontal and vertical asymptotes, as well as removable discontinuities. We'll take a look at one example. So here our function is f of x equals x plus 4 over 2x squared minus 32. Our directions say to sketch the horizontal asymptote, vertical asymptote, and the actual graph from a table of coordinate points. We are on the lookout for any point discontinuities, and then we want to wrap up this graphing by writing the end behavior of the graph using infinity notation. So where I begin is really this task of finding any point discontinuities. It might seem like a strange place to begin in the process since we are trying to graph, but finding point discontinuities is easiest from the outset. So the way that we would do that is I want to factor any polynomial in the numerator or the denominator. And what we're on the lookout for is a cancellation. So I'm going to bring the function and I'm going to do that factorization. So my I first goes to the numerator, x plus 4. And there's not much to factor there because that's already a linear binomial. So I'm just going to leave it as it is. However, when I look at the denominator, 2x squared minus 32, immediately I see that the coefficients 2 and negative 32 share a factor of 2. So I just pick up there and factor out 2. What that leaves me is x squared, and then negative 32 divided in half is minus 16. What that reveals to me is I now have a difference of 2 squares, x squared minus 16. So I'm going to carry the factorization out one more step. So the parts I didn't change are x plus 4 and the 2. But x squared minus 16 can be factored as x plus 4 times x minus 4 using the difference of 2 square patterns. Now, when I do that factorization, automatically I see I have an identical binomial above, x plus 4, same x plus 4 below. That I can divide and cancel. So the division is going to leave a 1 in my numerator and 2 times parentheses x minus 4 in my denominator. So I will rewrite the function to show that simplified form. And that's basically what I'm going to work with to continue graphing. But again, my reasoning for factoring wasn't to simplify the function so much as it was to locate point or removable discontinuities. And I've got one because I had a cancellation of a binomial. Really, cancellation of any variable would represent a removable or point discontinuity. So let's locate it. To locate a point discontinuity, once you've found that place, spell that correctly, discontinuity. Once you've found the place where the cancellation is, to find the x value of the discontinuity, you take that factor that's been canceled, set it equal to 0, and then solve. So this one's easy to solve by subtracting 4. And immediately I see that my removable discontinuity is at x equals negative 4. So that's going to show up on my graph as really just a gap or a hole in the graph. So it's not something I graph immediately. I'm just going to kind of hold on to it. So we finished that one part. We got a simplified version of the function. So what I'll do is now kind of zero in on these horizontal and vertical asymptotes. So to do that, I'm going to bring the function again. So the one we're looking at now is the simplified 1 over 2 times x minus 4. To find horizontal asymptotes, I'm going to compare the high powers on x above and below. So there is no x in my numerator now. So that's an implied power of 0. compared with the high power of x in denominator is power of 1. So clearly the high power is in the denominator. Now, why do we make that comparison? If I see that my high power is in the denominator, the way the function is going to behave in terms of a horizontal asymptote is that it will get closer and closer and closer to the x-axis. And that's really the case when the high power is in the denominator. My horizontal asymptote is the x-axis, and we can even think that that is the default position of the horizontal asymptote. So I'm going to sketch it there. It's the line right here on the x-axis. So I'll sketch it kind of a dashed line in blue there. It's got the equation y equals 0. Next, we want to locate our vertical asymptote. So the vertical asymptote is entirely eyes on the denominator. So I'm going to bring the simplified denominator to x minus 4. And what I do is I set the denominator equal to 0 and solve. And basically, when we do that, what we're finding is a place where algebraically the function would be undefined. So I'm going to solve this one. I'm going to divide the 2 over, and it just disappears into the 0. Cancels on the left. The right remains 0. 0 divided by anything except 0 is itself. And then I'm going to add 4 over. And right away, I get this equation for my vertical asymptote, x equals positive 4. So I'm going to graph that one. That is a vertical asymptote passing through the x-axis at positive 4. And that really kind of fleshes out the structure of my graph. So at this point, we're ready to plot that actual graph. So I need to create room here for a table. And let's calculate this table manually using our simplified function. So I'm going to put x. And I'm not going to go -2 through +2 because I really need to center my domain around the vertical asymptote. So if that one's at 4, I'm going to reverse to 3 and 2 and go forward to 5 and 6. I now want to write the function, so it's that simplified one, 1 over 2 times x minus 4. And let's calculate. So at 2, I'm going to plug in 2 for x, so it's 1 over 2 times parentheses 2 minus 4. That is the value of 1 over 2 times -2, which is -1/4. At 3, I'll substitute 3 for x, so 2 times parentheses 3 minus 4. That's negative again, 1 over 2 times -1, -1/2. Now 4 we had said should be undefined. It should be our vertical asymptote. Let's see if the algebra supports that prediction. So it's 1 over 2 times quantity 4 minus 4. There's our 0. 1 over 2 times 0 is 1 over 0. And I'm going to interpret that is undefined. And I've already sketched it in as a vertical asymptote. On the right side of the vertical asymptote, I've got the x value of 5. Plug that in for x. That gives me 1 over 2. 5 minus 4 is 1, which is +1/2. You can see that symmetry around the vertical asymptote. Same number, opposite sign. This is an odd function. 1 over 2 times quantity 6 minus 4. It's going to be 1 over 2 times 2, which is +1/4. So you see that symmetry repeated there. Well, let's plot our function. So I'm going to graph these points. It's underneath the x-axis at 2. Not far, but it's at -1/4. At 3, it's -1/2. So there's that left piece of the rational function. I'm going to re-sketch because I veered to the left there and it looked like it made it not a function almost. That's better. And then to the right, at 5, we have positive 1/2. At 6, we have positive 1/4. And that gives us the second piece of our rational function up in quadrant 1. The last thing is really to apply what we did at the very beginning. So at the very beginning, recall we had found a removable discontinuity at x equals -4. So the way to show that is to erase a small gap there and put an open point at that x value. That is much exaggerated. If I were to look on a graphing calculator, I wouldn't have that open point. It, in fact, would look continuous. So on a graphing calculator, you wouldn't see that removable discontinuity except in a table. And like our y value at +4, it would show up as undefined. So that finishes graphing. We've got our function plotted here with its removable discontinuity, its horizontal asymptote, its vertical asymptote. Our last task here is to record the end behavior. So remember, our usual question for end behavior is what's happening to y? What's happening to y? And it's really at the extreme left and right of the graph, what's happening to y. So as I look both on the left and on the right extremes of the graph, what I'm noticing is that the y value is getting closer and closer and closer to the x-axis. So it's not going nosedive down towards -infinity. It's not rising up towards positive infinity. It's evening out. And that's very typical of rational functions at the x-axis. So the way that I would record that, and it looks the same left and right, is as x approaches -infinity, that's the one on the left, y approaches 0. And really it's approaching its vertical or its horizontal asymptote. So notice the number should match your horizontal asymptote equation. And then similarly on the other extreme, as x approaches the far right, which is positive infinity, still y over there is approaching 0. And that completes our tasks here. Just to recap, we've graphed the function. We started out by looking for removable discontinuities by factoring the numerator and the denominator, see if there's any cancellations. If there are, you set them equal to 0 and solve, and then hold on to them. We then found our horizontal asymptote because here the high power was in the denominator. And that was at the x-axis, which is the default position for horizontal asymptotes. We found our vertical asymptote by setting the simplified denominator equal to 0 and solving. That told us that we had a vertical asymptote at x equals 4. And then we graphed our function by making a table of coordinate points and then fit in our removable discontinuity, which we found at the beginning, at the very end. And then we wrapped it all up by describing the end behavior, which typically for rational functions is equal to the value of the horizontal asymptote. Thank you for joining for this investigation of graphing rational functions with horizontal asymptotes. I'll let you graph your own rational function with horizontal asymptotes. Thanks for joining. See you soon.